problem 19.47, and it was this, which is basically if you have a 300 milliliter cup of coffee and it's at 90 degrees Celsius, if you put an ice cube at negative 27 at a negative 20 degrees Celsius in there, and you want it to get down to 60 degrees Celsius, then what will the mass of the ice have to be? So basically, you're finding the mass of the ice to get the 90 degrees to 60 degrees to get that 30-degree change in temperature. And I'll start off with what I found a little bit confusing. So like anything confusing, which was for me, I initially thought this was a conduction question. So I tried using the equation for conduction, and this is not what we're doing here. I did end up having to look at a mastering physics sample problem for this, where they explain how it's done, and then it really made sense to me, and then I kind of related it to one of the survey questions we got yesterday from the survey, and I'll get to that right now. So you have your coffee, right? So I listed all my variables. So your specific heat for coffee is 4190 joules over kilograms times Kelvin, and then your specific heat for ice is 2090, and you get this from the table in 19.2 in the textbook. And then your mass will be 300 grams, because 300 milliliters is the same thing as 300 grams. We did this in an earlier part of this class, early in the quarter. Your initial temperature is going to be 90 degrees. Your final temperature is going to be 60 degrees. And this is for coffee. For ice, the final temperature is the same because you're both ending at 60 degrees. But your initial temperature is negative 20 degrees because that's the temperature of the freezer, right? And if you guys remember from the survey yesterday, he gave us a graph of ice melting, right? And then you notice on the graph it goes down, and then it stays horizontal for a little bit, so it stays constant before going up. And this was because, if you remember, I don't know if this was in chemistry and physics or whatever, but during a phase change, temperature does not change. So like when you're going from water to ice, at one point you will stay at 0 degrees Celsius for a while, or like ice to water too. So to really get a feel for what this problem is that really, it's that graph. So you're starting at negative 20 degrees here for your ice, and then you're going up to 0 degrees Celsius, and you're staying constant. So you're changing from ice to water right here. And then once everything's changed, then bam, you're going up to 60 degrees because you're in the coffee, right, which is 90 degrees. So your temperature is going to rise. And your coffee is at 90 degrees, the temperature is going to go down to 60 degrees. So they kind of meet there. It's like a 0 point, equilibrium point. One's rising, one's falling. So then you look at this and then you realize that you have to use your thermal energies. So like the mass times the specific heat times the change in temperature. I use these for my last problem, 219.19. And you're also going to need the latency heat for ice, which I did not know, which I also got from mastering physics. So it's 334 kilograms over kilojoules. All right. So then you set all those equal to each other. Your thermal energy or whatever for ice plus your latency heat ice plus your thermal energy for water, because you are going to have water, because your ice will be water for a point after it's melted there. And then you're going to subtract your thermal energy for the coffee, and then you're going to set it all equal to 0 because it's going to equal the same temperature at the end, right? So then you would move the thermal energy for coffee over, and then on the other side where you have the water, ice, and all that, you can take out the mass because you have mass included in every single one of those variables. And the mass is going to be the same because, ice and water, it's the same thing. It'll have the same mass. So then after you take out the mass, you're going to divide both sides to get the mass by itself. And then you'll have the thermal energy of coffee over thermal energy ice plus latency ice plus the thermal energy of water. And then, again, don't forget, as you are multiplying these by your changes in temperature. So on top, your change in temperature for your coffee is going to be 30 degrees because you're going from 90 degrees to 60 degrees, so it's a change of 30 degrees. And then you are going to have, for ice, it's going to be 20 degrees. Yeah, it'll be 20 degrees because you're going from negative 20 degrees to 0 degrees Celsius. And then for water, it's going to be 60 degrees because you're going from 0 degrees Celsius to 60 degrees Celsius, right? You could just look at this graph again right here. This will be your change temperature ice, 20, constant. Now you're at 0 degrees for water, go up 60, go down 30 for whatever. So at the end, you plug all those in, you'll get like 37,710 over 612,750. And you get 0.0615 kilograms, which is 61.5 grams. And that's kind of it. And I guess like another thing, pretend this is like your coffee, right? I don't have coffee, but it's lemonade. So like, I don't know, let's pretend that this is like, I don't know, 61.5 degrees grams, and this was 90 degrees Celsius. Well, guess what? Now it's going to drop to 60 degrees Celsius. Yeah. Examples. Let's go. All right. Thank you. Sorry, this video is long. Please don't flag me.